Every single major automaker on the planet has spent the last decade fighting the same war. Range, charging infrastructure, battery chemistry, that's the battlefield, that's where the billions went. That's what every headline screamed about. And while they were all staring at the same scoreboard, measuring kilowatt hours and supercharger speeds, a particular company walked quietly into a different room entirely and rewrote the physics of how electric motors work. Not incrementally, not with a software patch, at the hardware level, at the materials level, at the level where once someone moves, everyone else is suddenly years behind and doesn't even know it yet. This isn't a story about a faster car, it's a story about a fundamental shift in what an electric motor can physically do, and what it means that only one company on Earth currently knows how to build it at scale. Here's the part that should stop you cold. The motor at the center of this story, the one that just humiliated every performance car on the planet, is small enough that a single person can pick it up and carry it across a room. One person, no crane, no forklift. And that motor, which you could tuck under one arm, just made million-dollar supercars look slow. If you think you already understand how significant that is, stay with me because the story behind it is stranger and more important than the record it broke. If this kind of breakdown is what you're here for, consider subscribing and hitting the notification bell. Every video on this channel goes exactly this deep. Now let's get into it. To understand why the carbon-wrapped rotor matters, you need to understand what every electric motor before it was fighting against, not competing against, fighting against physically. Picture this. Inside a high-performance electric motor, there's a heavy cylinder packed with copper windings and powerful magnets. Now, picture that cylinder spinning at speeds that make a dentist's drill look relaxed. We're talking 16 to 18,000 full rotations every single minute. At that speed, every gram of material inside that rotor is being flung outward constantly. The magnets want to fly out, the copper wants to expand, the whole assembly is under violent continuous stress, and that stress doesn't grow in a straight line. Double the speed, and the force trying to tear the rotor apart doesn't double, it quadruples. It's not just fast, it's destructive. To hold it all together, motor engineers for decades used a containment sleeve, a tight wrap of high-strength metal around the outside of the rotor, usually steel, sometimes inconel, the same exotic alloy used in jet engine components. These are strong materials, expensive materials, and, well, they worked, but only up to a point. That point was around 16 to 18,000 revolutions per minute, beyond which the sleeve itself couldn't hold, and the risk of catastrophic failure became real. That ceiling defined an entire generation of electric vehicles. It wasn't a design choice, it was a physical constraint baked into the properties of the metal itself, and honestly, the entire industry accepted it. But there was a second problem, one that's arguably worse and almost never talked about in plain terms. Steel and those exotic alloys aren't just strong, they conduct electricity, and here's where it gets interesting. When you spin a conductive metal sleeve inside a powerful rotating magnetic field, the field creates electrical currents inside the metal itself, circular currents that go nowhere useful. They don't help the motor spin, they don't charge the battery, they don't move the car, they just churn through the metal and turn into heat. Useless, unavoidable, invisible heat generated constantly every second the motor's running, regardless of how hard you're pushing it. You could build a motor for raw peak power, brutal launch, breathtaking acceleration, but the heat would build fast, and the car's computer would quietly cut the power after a run or two to protect the hardware. Or you could build for efficiency, optimized range, consistent everyday performance, but you'd sacrifice the performance ceiling. Power or efficiency. Pick one. The physics of the metal sleeve made choosing both impossible. Every high-performance EV you've ever seen was built by engineers working brilliantly within that trap. One automaker built an entire two-speed gearbox to work around the RPM ceiling. Another engineered some of the most efficient motor windings ever put in a production car. Real achievements, both of them. But they're both optimizations of a fundamentally limited design. The same ceiling, the same trade-off. The company's question wasn't how to optimize within the constraint. The question was, what if we just got rid of it? The answer was carbon fiber, not the kind you see on a sports car hood or a bicycle frame, a specific engineered application developed through a winding process that didn't exist anywhere in the industrial supply chain. The company had to invent it. Okay, so here's what they did. They built a proprietary machine, designed and built entirely in-house, that winds aerospace-grade carbon fiber directly onto the rotor under, enormous tension. The finished sleeve is just half a millimeter thick. Seriously, you could stack 2 of them and they'd still be thinner than a credit card. And that sleeve is more than 5 times stronger than the high-grade steel it replaced, 5 times stronger at just a fraction of the thickness. But honestly, the raw strength number isn't even the most important part. The way the fiber is wound is the real secret. Because it's wound under tension, the finished sleeve doesn't just passively hold the rotor together, it actually actively squeezes it before the motor has turned a single revolution, before a single electron has even flown through it. The rotor is already being held under compression by the wrap. Think of it like wrapping a barrel so tightly that the barrel itself is being squeezed from the outside before you've even put anything inside it. It's a layered defense, and it works so well that the motor just sails past the 20,000 revolutions per minute wall that stopped every previous design, and potentially even higher in future versions. That RPM sealing the industry treated like a law of physics for a decade. Yeah, it wasn't physics. It was metal. Change the material, move the sealing. But here's the part that really changes everything else. Carbon fiber doesn't conduct electricity. The moment you replace the conductive metal sleeve with a non-conductive carbon one, those eddy currents, the invisible parachute dragging on every previous motor, have no medium to form in. They don't get reduced. They don't get managed. They just disappear. The waste heat that was robbing efficiency and basically cooking the motor from the inside simply ceases to exist. The effect is immediate and honestly, pretty dramatic. The motor runs cooler under repeated hard acceleration, not because of better cooling systems, but because it's generating dramatically less waste heat in the first place. More of the battery's energy actually makes it to the wheels instead of bleeding away invisibly. The power output stays consistent, run after run after run. And there's a third effect, quieter but just as important. The carbon sleeve is so thin that the gap between the rotor's magnets and the surrounding windings shrinks significantly compared to a metal sleeve. A tighter gap means a stronger magnetic interaction between the two halves, which means more torque, more power from the same size motor. You get a massive jump in power density, a motor that's smaller, lighter, and yet far more powerful than anything built before it. 3 improvements all at once: higher RPM sealing, eliminated waste heat, stronger magnetic output. And the reason this matters so much is that these 3 things work together and actually amplify each other. Higher RPM is more valuable when you're not thermally limited. Better thermal performance becomes more valuable when you have more RPM headroom to use. Higher power density becomes more useful when you can sustain it consistently. You don't just add these benefits, you multiply them. This is why nobody else has matched it. It isn't one breakthrough you can copy. It's 3 breakthroughs that only work together if you've also solved the manufacturing challenge of the carbon winding itself. And, honestly, that manufacturing challenge is where the real advantage lives. Now, let's put this into the car that actually proved it. We're talking about a particular 4-door family sedan, 5 adults, luggage, enough battery for real daily driving without anxiety. A car you could take your kids to school in on a Tuesday morning, and 3 of these carbon-wrapped motors producing a combined 1,020 horsepower. Torque at the wheels approaching 14,000 Newton-meters, a figure that, honestly, belongs on a loaded freight truck, not a car one person can carry under their arm. 0 to 60 miles per hour in under 2 seconds by any honest, real-world measure.